slightly more complicated situations involving not just one event, but two events. And both situations we'll look at will involve picking a card or cards from a standard 52 card deck. So if you're not familiar with a 52 card standard deck, there's one in front of you, so you should familiarize yourself with the structure of a deck if you're going to continue studying probability, at least in this video and probably subsequent videos as well. So the first problem we'll look at is a gambler, and a gambler draws two cards from a standard deck with replacement. What's the probability that she draws two aces? And what makes this a little bit more of a, complex situation is the gambler's not just picking a single card, but the gambler's picking two cards. So there's actually two separate events to consider. Event A is a gambler will draw an ace on the first draw. That is the favorable outcome we're looking for. And then event B, the second event, is drawing an ace on the second draw. Keeping in mind, an important thing to keep in mind that the gambler has replaced the first ace. So event B is draw an ace on the second draw after replacing the first ace. So when you're dealing with more than one event chained together in probability, it's really, really important to consider the effect of that the first event has on the second event or any other subsequent events after that. So always ask yourself, does the probability of the first event happening have any effect on the second? Before we deal with that, let's just remind ourselves, the basic working definition of probability. Now I have an intersection symbol there, and you might not have seen that for a while. So this is the probability of both of these events happening, so A and B. We'll focus on that a little less at the moment, and let's just remind ourselves of the user-friendly, working definition of probability, which is simply if we can figure out the number of favorable outcomes we're looking for, we can divide that by the number of all possible outcomes, or the total number of outcomes. So how do we do that? Well, we can figure out the total number of outcomes, possible outcomes, by considering the number of ways that you can select two cards with replacement. So we'll put a couple of decks in front of us here in a second, and this total number of ways, of course, will be the, cardinality of our sample space here, or the number of elements in our universal set, the denominator in our probability calculation, for lack of, a better word. Anyway, here's our two decks. So if we consider there's 52 possibilities of selecting a card on the first choice, and of course if you're going to put that card back into the deck, there's 52 choices on the second one. So hopefully your fundamental counting principle is jumping out at you there. So for any of those 52 cards you get on the first choice, you can pair it up with 52 cards in the second choice. So that is 52 times 52. Those are the total number of outcomes, and that's the size of our sample space. And now for the number of ways of selecting two aces with replacement, then we just have to consider how many ways we can pick an ace in the first choice. This is going to be our numerator in our probability calculation, the number of elements that's in our A and B set. And of course, I'm dealing with set notation here in the midst of our user-friendly probability definition of favorable outcomes divided by total. So this is going to be our numerator, and of course, there's going to be four aces to pick on the first choice. And since we're going to put that ace back, if we happen to get an ace on the first choice, which is what we're counting here to actually get an ace on the first choice, if we put it back into the deck, there's going to be four more aces, at our disposal. So the number of ways of choosing two aces going to be 4 times 4. Again, our fundamental counting principle is the glue that's holding this calculation together. And that would mean there's 16 possible ways that we can choose two aces from a deck of cards. So, number of ways of selecting two aces, just to remind you, if you're wondering how that is 16, maybe to help you visualize that, before we get to our actual probability calculation. I took the time with some lovely graphics there to show you that if you get an ace of hearts on the first choice, then of course we can cycle through the other 4 aces in the leftmost column there. And of course that gives you 4 possibilities. And then you can have an ace of diamonds for your first choice. Cycling through your remaining aces gives you 4 more, and similarly with the ace of clubs in the first choice, and then the ace of spades. So there it is in front of you, showing you the 16 different ways that somebody could actually select a pair of aces and two choices or two selections from a standard deck of cards. So now let's get to the actual probability calculation. But before we do that, I forgot to mention this note here as well, that when you see with replacement, that should be bringing back, I guess, some familiarity with our counting methods that we've already covered earlier in this course, where repetition is either allowed or it's not allowed. So if you have with replacement, then that means you can repeat, and repetition is allowed, which is really the same thing. And that symbol with the three lines just basically means those two things are equivalent. So for example, you can have a pair of ace of hearts, you can have a pair of ace of diamonds, a pair of ace of clubs, and a pair of ace of spades. That's possible only with replacement, because of course the repetition of the aces is allowed. So now get to the probability calculation. And here's our working definition again. So let's just establish that right now we know the total number of outcomes is 52 times 52. Possible ways we can pick any two cards from the from the standard deck. And then the pair of fours multiplied, of course, are the number of ways that we can select specifically two aces from a standard deck. Again, that's with replacement. And you can probably recognize that we can pull those, I guess, the numbers in the top and bottom of a fraction, apart and write that as two separate fractions. And this is, I guess, probably the best way to be calculating a probability. If you're dealing with two events, really what you need to do, and the fundamental counting principle has led us here, that if you can calculate the probability of getting an ace out of a deck of cards, that's your first choice, and you simply just have to chain it together with the second choice, probability of the second choice, using multiplication. And of course, it's the fundamental counting principle that allows us to do this. So the pair of 4 out of 52s represents, I guess, the equal likelihood of selecting an ace on the first or the second choice, because of course we're putting the ace back and reshuffling the deck. And this is an important concept. And so if you're going to multiply, if you're able, I guess, to simply multiply a couple of events together, two in this case, and the first event has no effect on the second event, because we can see the probability of getting an ace on the second choice is the same as it was on the first. And of course, that's a result of replacing the deck. And if that happens, we have independent events. Now, we'll deal with independence a lot more later in this chapter, but for now I think it's important to at least consider what we mean by independent events. And even when you're doing some of these easier probability calculations, to always ask yourself, when you're chaining events together, does the first event have any effect on the second? And so of course we can finally get to our punchline here, which is actually not my main focus. This idea of independence is really the main focus of this first example, but there's our numerical answer. A pair of 4 out of 52s can reduce to 1 over 13. So a pair of 1 over 13s multiplied together gives you 1 over 13 squared, or 1 out of 169. So it's not really likely to get a pair of aces in particular on two draws from a standard deck with replacement. You would expect it to happen on average once in 169 attempts. Okay, so now for our second example, which seems it's almost identical to the first, and it is very close, but of course the key wording is this idea of now without replacement. So what happens if the gambler draws two cards from a standard deck, as we just looked at, except now instead of replacing the ace, you are not allowed to replace it, you keep it in your hand. So without replacement, what's the probability that he draws two aces? So of course we still have two events in this problem, and I guess event A is drawing an ace on the first draw, and event B is drawing an ace on the second draw, now without replacing the first ace that you have in hand. So we have to now, of course, just like we did earlier, we have to figure out the total number of possibilities. I'm picking any two cards in a sequence without replacing it in a deck of cards. So we could, and this is going to be our denominator in our probability, which is the total number of, items in our sample space, or the total number of possibilities. And now we can visualize our entire first deck is available for the first choice. And then for the second choice, I just blotted out one card there, the King of Diamonds. Hypothetically is what we picked on the first choice, but just to remind you that if you don't replace your first selection into the deck and reshuffle, then of course you're missing a card for that second choice. So the first selection has had some effect on the second selection, so that is definitely different than the first example we looked at. So the total number of ways of choosing any two cards without replacement from a standard deck is going to be 52 times 51, and again, that is our fundamental counting principle, holding that together. And then that sets us up for figuring out the total number of ways of selecting two aces without replacement. This will be the number of elements in this set, which is the numerator in our probability calculation. And don't let the A and B intimidate you too much. That's just reminding you that it's, I guess, we're looking for the convergence of two events to happen here at, I guess, not at the same time, but of course making sure that both of these events actually happen in sequence. So what's the number of ways of selecting two aces without replacement? Well, of course, we'll have 4 aces at our disposal for the first selection, and then if we're not able to put that ace back, we're down to 3 for the second choice. So now we're only limited to 12 possible ways we can select two aces if we do not replace our first ace and reshuffle the deck. And now that sets us up for our actual probability calculation. And just like last time, I forgot about to mention this slide to show you that, I guess, that small sample space that we just created, that subset of our 52 times 51. Here's the subset of selecting two aces without replacement. And of course, we're not able to repeat anymore. We can't have a pair of aces of hearts or a pair of aces or diamonds or clubs or spades because we aren't allowed to replace. And there's our 12 element subset. And of course, without replacement is in probability, at least in selecting cards or anything similar to that, is actually the same as when we weren't allowed to repeat earlier in specific counting problems. And of course, the fact that we're not allowed to repeat means we can't have the same ace 2 times in a row in this case. So now we'll get to our actual probability calculation. So the probability of getting two aces now without replacement is going to be 4 times 3 is the number of ways of selecting two aces divided by the 52 times 51, which is the number of ways of picking any two cards without replacement from a standard 52 card deck. And of course, we can pull those numbers apart in the numerator and denominator, and we can see probably a more user-friendly way of calculating these two chained probabilities, these two different events happening in sequence. So the 4 out of 52 is getting an ace on the first choice, and if we don't put the card back, we only have 51 cards to draw from, and there will only be 3 aces guaranteed to be in that deck for the second choice, because remember, there's one sitting in your hand. So clearly, it's not drastic, but the first selection has had some effect on the second selection. So we don't have independent events. We call these things dependent events. And I'm just kind of showing you the notation now, and we'll read through it. Don't get too intimidated by it. At first glance, it does look a little bit, I guess, abstract and complicated, but if you read it along with me, the probability of A and B is the probability of A, and that's the 4 out of 52 in this example, multiplied by, and this vertical line means keeping in mind or given that. So the probability of B given that A has already occurred. So keeping in mind that A has occurred is telling me that it must have had some effect on the probability of B. So what that means, when you look at the I guess, choosing an ace on the second choice, you're not going to say 4 out of 52 anymore, because you're keeping in mind or given that you already have an ace in your hand. And that's what that so-called conditional probability of B giving that A is reminding you of. To keep in mind you have an ace in your hand, so don't say you have a 4 out of 52 probability on your second choice. You now have to make an adjustment, now 3 out of 51, which doesn't change things a lot, but of course it changes it some, and we're interested in getting the correct answer, of course. So that's going to give us a punchline now, which is a little less likely to get 2 aces if you're not going to have the same probability on both selections. Your second probability is slightly less than your first. So in 221 attempts on average, you would expect to get a pair of aces once if you are not allowed to replace the card, or if you choose not to replace the card. Okay, just in case you're a little overwhelmed with, I guess, some notation and terminology with independence and dependence and conditional probability and B given A has occurred, let's just, I guess, tone things down here a little bit as we wrap up this video by looking at two very similar examples to what we just dealt with, but I guess a little bit more elaborate, and I think just to show you what you really need to know out of all this. So a gambler draws 4 cards from a standard deck with replacement. What's the probability that she draws 4 face cards? So this isn't a 2-event question anymore. This is actually a 4-event question, since there's 4 choices or 4 selections from a standard deck. And I guess we could start saying events A, B, C, and D, but I think that would take so long to write out, and I don't think it'd be very useful either. You wouldn't even know what letter B represented after a few minutes, I don't think. So let's just say the probability that we get 4 face cards. A written description is as good as any, I think, especially when there's more than 2 events, maybe even when there's more than 1 event. So probability that you get 4 face cards. Now, of course, don't have to rewrite the whole question in there, but just keeping our eye, I guess, on what we're trying to calculate. So those are 4 different events that we have to determine the probability of. So we're going to multiply those 4 probabilities together. And remember, we're able to do that because of the fundamental counting principle is the glue that's holding this all together. So how many face cards are there going to be in our full deck of 52 cards? And if you hopefully know, there's 3 face cards, a jack, a queen, and king in each of the 4 suits. So that would give us 12 face cards in total that we can pick in our first choice out of a deck of 52. And then the key, of course, in all of this in the bold font here, is that with replacement, we put that face card back in the deck. Of course, we should shuffle it, so make sure that all cards are equally likely on the second choice, and we still have a 12 out of 52 probability on the second, on the third, and on the 4th selection. So this probability is staying the same on each of the 4 selections here. So of course we are dealing with independent events. Now that's a term that you should get very familiar with. If you have independent events, you're dealing with independence. Your probability, you can just chain them all together and multiply, and you don't got to worry a whole lot. But that being said, you probably should still worry some to ask yourself when you write down the probability on the second, third, and fourth selections. Just ask yourself, what's the situation? Oh yes, I'm having all 52 cards are at my disposal, so my probability is staying the same each and every time. So of course, since we have independence here and our probability is the same 4 times in a row, we can just type this into our calculator and write that either as a fraction or a decimal or a percent. Okay, so let's type that into my graphing calculator here. So 12 out of 52 to the power of 4 multiplied by itself 4 times. And then we realize that's not terribly likely, but I guess we could say it's a 0.002836 in decimal form. Or we could times that by 100 and say that is less than a percent, 0.2836%. So we're roughly 1/4% there. It's not extremely likely to get 4 face cards in a row. Okay, and to round out this video, same question as last time, but with one important difference, that we're now dealing without replacement. So we'll see that our probability is not resetting every single time. So let's just get set up first to say, okay, I'm going to try to figure out the probability of getting 4 face cards. So whether you want to define that using 4 letters in events, but I think this is probably most efficient way. And then say, okay, on the first choice, nothing changes from the last calculation. It's 12 face cards out of the 52 cards. And now I'm not going to say 52 cards anymore because I have one of those face cards in my hand. So now I only have 52 cards to choose from, and I only have 11 face cards left in the deck. And of course, numbers start counting down, and you're probably flashing back to counting methods questions that involved repetition not being allowed, and of course numbers started counting down when that happened. Or in this case, just say, okay, every time I pull out a face card, I keep it. So my denominator keeps decreasing by 1, and so does my numerator. So now in the third choice, there's only 50 cards left in the deck, and only 10 face cards left in the deck to choose from. And then we're down to 49 on the last choice, and there's only 9 face cards left. So if we multiply all those fractions together, we'll have, I guess we'll go straight to a decimal representation, possibly a percent again. And we would expect this one to be a little less likely than last time, because of course our probability is decreasing each and every selection. Okay, so we'll type this into the graphing calculator here, and if we're multiplying and dividing here, we don't have to worry about brackets, so just type away. 12 out of 52 times 11 out of 51 multiplied by 10 out of 50, and of course I could have reduced that, but I guess I'm not going to worry about it. Multiplied by 9 out of 49, and there's our decimal representation, 001828. Okay, so there's our decimal representation. Of course, if we want to times that by 100 again, we could say that is a smaller probability, around 0.2 or 0.1828%. So please don't get confused with that decimal percent. Sometimes students read that and think that means 18%. If it doesn't, it means you have less than 0.25% there now, or less than 1/5. You have 0.18%. So it's very unlikely to get 4 face cards in a row, and note that that probability is slightly less than the last calculation, and that's what without replacement does. It limits your choices, and it decreases the likelihood of getting 4 face cards in 4 choices. Okay, so that rounds out our video on dealing with pretty much just 2 events. And of course, I snuck in 4 events there just to illustrate that your line of thinking and reasoning doesn't need to change. Just keep in mind you're able to multiply probabilities together, whether events are independent or, in this case, dependent events. Just ask yourself every step of the way as you multiply those probabilities, make sure you're clear on what the situation is and whether your probabilities are staying static each and every time, or in the case of dependent events, you're seeing your probabilities go down when you are choosing cards over and over again from a standard deck without replacement.